low pass filter. Right? They got the image like this. Is it clear? Similar to the original image? No. Ultimately, there is no much difference before and after the application of the filters. Right? So can we better improve the performance of the filters? Yes. How? Using nonlinear filters. Okay. So one such nonlinear filter is we call it as a median filter. It's a very popular filter used for research in the 2K 2000 year, right? In the year 2000, this median filter was very popularly used in many research problems as one of the very popular pre-processing technique to remove the noise. One of the popular pre-processing technique in image processing before 2000, before the year 2000 was this median filter, right? So it simply replaces the pixel value with the median value in its neighborhood, right? You know what you mean by a median value, right? Mean, median, mode. You might have studied the three quantities.
Yes, sir. Yes, sir. Yes, sir.
Mean, median, mode, right? So this particular filter is called as median filter because it takes the median value from its neighborhood, right? So through this filter, it is a good choice for a short, heavy-tailed noise, as the median value is not affected by the extreme noise values, right? Extreme noise. Say for example, uh, if you consider this 3 cross 3, right, which I have highlighted here, 1, 3, 7, 3, 4, 8, 4, 5, 7. Is it visible? Visible now? 1, 3, 7, 2,
Yes,
4,
sir.
8,
Visible, sir.
4, 5, 7. If you arrange these values in the order of increasing order, and if you find the median will be 4, right? So this particular pixel will be replaced with 4, right? So it can be computed in linear time, which reduces the blurring of images, right? So you please see the difference between this image plus short noise and then Gaussian low pass filter, and then with respect to the median filter. Anyhow, median filter, when we apply median filter, there will be certainly some loss of information. Certainly some loss of information due to median filter. But anyhow, the noise got removed. Noise got removed. Okay. So here is the while averaging minimizes the square deviation, median filtering minimizes the absolute error. Okay. And bilateral filters. This is also a very important nonlinear filter. So Gaussian filter, which we have studied in the previous slides, which provides a nice way of grading the weights of the neighborhood pixels, neighboring pixels, right? Either through probability distribution function or by a 5 cross 5 kernel, right? This Gaussian linear filter provides a nice way of grading the weights of the neighboring pixels, right? So that the closer pixels will have more influence than the distant pixels, right? But median filters provide a nice way of reducing the influence of outliers, right? Outliers means, suppose if you say a neighborhood, right? That neighborhood have the values like 4, 5, 7, 9, and one more pixel as 125, right? This 125 is treated as an outlier, right? And this 125 will be replaced with the median value, right? That is the duty of median filters, right? Reduces the influence of outliers. Are you getting my point? Please get the difference between Gaussian linear filter and median filter. Gaussian
Okay,
filter
sir.
provides a good way of approximating the neighboring pixels, right? So that the closer pixel will have more influence, whereas a distant away pixel will have less effect on the current pixel. That is what linear filter is. And this median filters, which provide a nice way of reducing the influence of outlier values, right? So can we combine these two positive effects of Gaussian and median? right? Then we call it as bilateral filters. Bilateral filters is the combination of Gaussian linear filter and median filter, right? That is why it is called as bilateral. This combines the benefits from the linear filter and also from the median filters. Okay.
Okay, sir.
So this bilateral filter, the output pixel value depends on the weighted combination of the neighboring pixel values. Weighted combination of whether we will take neighboring pixels. At the same time, we will also see the weighted combination, right? Weighted combination, right? In 4 possible directions we will see, right? For a given image at a given pixel position k comma l, right? For a given image f at a given pixel position k comma l, we will apply a weight in all the 4 directions I, j, k, l. Right? We will see the 4 neighboring pixels in all the 4 directions, right? If there is a pixel, it will be surrounded by 4 pixels, right? That 4 pixels, like you might have seen here, right? 1, 0.8, 0.8, 0.8, 0.8, right? This is how this I, j, k, l comes into picture, right? So the weighting coefficient depends on the product of the domain kernel, right, and the data dependent range kernel. There are 2 kernels we are defining here. One is the domain kernel, another one is the range kernel. This domain kernel gives what type of object in that particular neighborhoods, right? Whether the neighborhood represents a single object or the neighborhood represents multiple objects, right? That is what we call it as domain kernel. Right? From this we generate a weighting coefficient, right? And that is represented by d of ijkl, and a data dependent range kernel. Data dependent means, so you see 1, right? What are all the values which are all very closer to 1? 0.8, right? That 0.8 will be selected. You're getting my point, right? 0.4 are neglected, whereas 0.8 is selected. That is data dependent range kernel. So there are 2 kernels will be designed. One is the domain kernel and another one is the range kernel. So when multiplied together, you will get a data dependent bilateral weight function. This is one weight function. This is another one weight function. If we multiply these 2 weight functions, then we will get a data dependent bilateral weight function, that is wijkl, and that is given here wijkl. Okay. So which combines the effect of both domain as well as data. So is this SID? So there is an input image, right, which looks like this, and there is a domain kernel which yields a normal curve, right, and there is a range kernel, right, which smoothens the image, right, and finally if you apply both this domain as well as range kernel, you will get a bilateral weight function W. If you apply this bilateral weight function over this input image F, that is F and W, right, are getting multiplied, right? F and W are getting multiplied for each pixel position. Finally, it's add up for all the, this is applied for all the pixels k comma l, kth row and lth column. Okay, then we will get a very good output image, right? Basically, the purpose of these uh, filters are to remove noises, right? Anisotropic diffusion, right? It's not in the syllabus. Anisotropic diffusion. Anyhow, you please try to understand what you mean by anisotropic. Hello, Sarthak? Sarthak?
Hello, sir. It's Siddharth, sir.
No, Sarthak just entered now. Sarthak.
Yes, sir.
Uh, the class also he left. You passed some comments, right? About me, laughed twice or thrice. I don't know what is. Even you, after that, you didn't come and meet me. You go your way, I come my way. Yeah.
No, sir. Nothing like that, sir.
Whether your friend is available now. Number one, the great man, Sriram. Sarthak, please check whether your friend is available. Sriram. No.
Sir, I don't know. Apologies for coming late, sir. I had gone to eat food, so I left my phone in the room. I just came back.
No, Siddharth. Okay. No
Yes, sir.
problem.
Yes, sir.
So now I am asking that number one register number, Sriram. Sir, is available. No. Okay. So basically, anisotropic diffusion, that means the iterative application of this bilateral filtering which leads to their smoothing process, right? I think in physics you might have studied about anisotropic diffusion. Any idea? In physics, the diffusion of the light signal in different medium, isotropic and anisotropic diffusion, right? Don't know whether you might have studied or not.
Yes, sir. I guess we studied this in school.
Edge preserving smoothing technique, that is what you have learned in physics. That is also applicable to this image processing, in which we preserve the edges. When we perform smoothing operation, please listen carefully. This is a very fundamental point in image processing and computer vision, right? When we try to smoothen an image, we lose information, right? Especially the edge information. When we try to smooth an image, we lose the edge information, right? When we try to sharpen an image, right, edges get very clear. Get very clear. But in the case of sharpening, we may lose the internal information with respect to an object in an image. Internal information. Say, for example, if we smoothen an image which has wall clock, right, we may lose the border of the wall clock. If the wall clock is round, right, we may lose its border. But we can identify what is the time within that wall clock. But when we sharpen an image, right, what happens is we will get the circumference of that wall clock, circular wall clock, very clear. But we will lose the inner details in the wall clock. Right? This is a very simple example to make you to get the difference between smoothing and sharpening, right? But when you want to do smoothing and also preserve the edges, right, then we call it as anisotropic diffusion. Okay, that's all. But there are so many mathematical equations not required, right? So anisotropic diffusion